Hello, my name is Qiqing Tao. I'm a postdoc researcher at Dr. Sudhir Kumar's lab in Temple University. I want to thank the organizer for the opportunity to share my work. Today, I would like to talk about data-driven speciation tree prior for better species divergence times in calibration-poor molecular phylogenies. As we all know that node age estimates are products of interaction between calibration time priors and speciation tree prior. To get better node age estimates, we can use more precise calibrations. However, in most cases, fossil record is incomplete and sparse, so there are many calibration-poor lineages in tree of life. To date such lineages or phylogenies, the specification of tree prior becomes more important. Basically, the tree prior describes the density distribution of the node ages. The use of different parameters of the tree prior will lead to very different density distributions and also the time tree structures. As the example shown here that the time tree simulated using the flat tree prior looks very different from the time tree simulated using the skew tree prior. There are more long branches in the trees that simulated using the flat tree prior, and more short branches in the tree that simulated using the skew tree prior. Unfortunately, no studies have investigated the impact of parameter settings of the tree prior in dating calibration-poor phylogenies. In fact, the default setting is often used in empirical analysis, which is a flat and uniform distribution. We don't know whether that is always a good choice or not. What if the density of the actual node ages is not uniform-like? Would that create any problems? So to investigate such issue, we simulated sequences using a skewed tree prior. As you can see that the density distribution of the simulated node ages is very different from what was specified by the flat tree prior. We only use the root calibration in this case to represent the minimum number of calibrations. From a scatter plot, you can see that the flat tree prior produced a very biased result, and all the times it estimated are really off. But for some reason, if you have some information about the tree prior, by using a correct informative tree prior, you can have much better time estimates. Then we simulated more data sets to check whether what we observed here is a special case or not. So we simulated 10 more data sets using a skewed tree prior, and then we calculated the mean absolute percent error, mean percent error, and HPD coverage probability for all the data sets. HPD coverage probability is the percent of nodes in which the estimated HPD intervals contain the true values. From the results shown here that you can see the use of flat tree prior produced very bad results, and it has a really high mean absolute percent error and a high mean percent error, meaning that the accuracy is low and the bias is high. And also the HPD coverage probabilities are low for all the cases, lower than 50% in general. So the flat tree prior did not perform well. But again, somehow if you have some information about the tree prior, then you can have much better results. You can significantly reduce the error rate for all the cases, and then have much higher HPD coverage probabilities at around 95%. So now the question becomes, how can we know the informative tree prior, or how to get this correct tree prior? So we developed a method to derive the values of parameters for birth and death speciation tree prior from molecular data. We call that as data-driven birth and death tree prior. Parameters can be estimated based on the relative node ages inferred using the relative rate framework without calibrations. Relative rate framework is a non-Bayesian method to estimate divergence times without the use of tree prior rate models or calibrations, and also it allows the rate variation among lineages. The parameters in the birth and death process, the birth rate, death rate, and sampling fractions can be estimated through a maximum likelihood procedure. by using the equations here. I won't go into too much details about how the parameters are estimated. If you're interested, I'm happy to take questions later. Now I would like to show you the result from the data-driven tree prior on the same simulated data that I have shown before. We can see that the use of data-driven tree prior has significantly improved the result. And compared with the flight tree prior, all the dataset have much lower error rate and much higher HPD coverage probabilities. Actually, if you compare what we have from the correct tree prior with what we have from the data-driven tree prior, we can see that the results are very similar. This means that the data-driven tree prior estimated using our method performed similarly to the correct tree prior. This is very encouraging. Then we applied our method to an empirical dataset that contains 12 genes from over 200 mammals. We did not use any calibrations, internal calibration in this analysis, so only the root calibration is used. And then we compare the times inferred using the flight tree prior and the data-driven tree prior with the published times. But the published times are obtained by using many well-constrained calibrations. We found that the use of data-driven tree prior significantly reduced the differences between the inferred times and the published times. This is because that the data-driven tree prior fit the fit the distribution of node edges, which is a gray bar here, much better than the original flight tree prior. And then we applied a few well-constrained calibration along together with the data-driven tree prior. We used the 1 to 4 well-constrained internal calibrations, which is about 10% of the original calibrations. We found that the use of internal calibrations reduced the differences between the inferred and the published times. This is expected because the calibration can constrain the posterior times. But again, the data-driven tree prior performed better than the flat tree prior. It produced the times more similar to the published times. And also the HPD intervals produced by the data-driven tree prior contains the published times more often. This result means that the use of data-driven tree prior can potentially reduce the need to have many calibrations for good time estimates, because by using a few calibrations and the data-driven tree prior, you can have time estimates close to the published times, which are obtained by using many calibrations. But in a lot of cases, we don't have that many well-constrained calibrations. So we relaxed the calibration boundaries on the same calibrated nodes to represent the diffuse calibration case. And we found the similar patterns. The data-driven tree prior performed better than the default flat tree prior. It produced the time estimates more similar to the published times with the use of only a few diffuse calibrations. And the HPD intervals estimated using the data-driven tree prior contains more published times. So far, we have shown that the data-driven tree prior works well with the root calibration only, a few well-constrained calibration, and a few diffuse calibrations. In all scenarios, the data-driven tree prior can produce better estimates than the original default flight tree prior. But in all of those analyses, we used the correct tree topology and a substitution model. However, in reality, an incorrect substitution model may be used, and a tree that contains a lot of topological errors may be used to analyze the data. So we wanted to investigate the impact of model validation on our method. We reanalyzed the simulated datasets using an oversimplified substitution model, and also using the correct complex substitution model. And also we analyzed data using the inferred and the correct tree topologies, and of course with the flat and the data-driven tree priors. What we found is very interesting. Actually, the main determinant of the accuracy of time estimates is the tree prior. because the use of the data-driven tripwire always produces better time estimates than the flat tripwire. The mean absolute percent error rate is just much lower when the data-driven tripwire is used. Doesn't matter whether you're using an inferred or a correct tree topologies, simple or complex model. And interestingly, the use of the inferred tree topology that may contain a lot of topological errors only increase the error slightly compared with the correct tree topology, which means that the error in the tree topology only have a limited impact on the time estimation accuracy. And similarly, the use of a simple substitution model increases the error a little bit more, but much lower when you use a flat tripwire. So neither the use of a simple model or inferred tree topology would have a big impact as the use of flat tripwire. Therefore, the tripwire specification is actually the key determinant of the accuracy of time estimates in dating the calibration-poor phylogenies. And the use of the data-driven Bertrand tripwire can improve the accuracy and precision of divergence time estimation for calibration-poor datasets. And the use of the data-driven Bertrand tripwire reduces the need to have many well-constrained calibrations to get the reliable time estimates. I would like to thank my advisor, Dr. Sudhir Kumar, and my collaborator, Dr. Jose Robert Montoya, for their help. If you want to know more about the project or want to try the method, you're welcome to read the article or try the method that's already available online. Thank you very much.